Welcome to this video on transmission impairments in data communication and networking. We will explore the unwanted changes that affect signals during transmission. Signals traveling through transmission media often undergo unwanted changes, leading to weak or distorted signals. These unwanted changes are known as transmission impairments, which significantly reduce communication quality. The main impairment categories are attenuation, distortion, and noise. Attenuation is the loss of signal energy over distance. Distortion is the change in signal shape. Noise is unwanted electrical energy added to the signal. Section 01 focuses on attenuation, which is the loss of signal strength during transmission through the medium. Primary causes of attenuation include the resistance of the transmission medium, converting the signal to heat, long communication distances leading to cumulative loss, and signal absorption by the surrounding environment. The impact of attenuation includes weak signal reception, increased communication errors like bit error rate, and drastically reduced data quality and reliability. This can result in a significant quality reduction. To quantify the loss or gain of energy, engineers use decibels or dB. This measurement uses the formula dB equals 10 times log base 10 of P2 divided by P1, where P1 is input power and P2 is output power. Engineering solutions for attenuation include amplifiers for analog signals to boost power levels and repeaters for digital signals to regenerate binary pulses cleanly. Distance control also limits transmission segments to manageable lengths. Analog amplification boosts the strength of attenuated analog signals. However, a significant drawback is that it also amplifies noise along with the signal. Digital regeneration uses repeaters to regenerate digital signals, unlike amplifiers. This process cleans the signal by decoding it into zeros and ones, removing noise accumulation and retransmitting a fresh, clean signal. Section 02 is about distortion, defined as the change in the shape of a composite signal. Distortion originates from various factors, including propagation delays, where different frequency components travel at different speeds, channel imperfections like physical flaws, and bandwidth limitations that clip high-frequency components also cause shapeshift. Distortion significantly impacts reception by causing signal shape changes that make data unrecognizable. It creates difficulty in signal recovery at the receiver and leads to increased bit error rates in high-speed digital systems. Corrective measures for distortion include equalization, which uses electronic circuits to compensate for delays and attenuations. Using quality media, such as fiber optics, minimizes internal delay spread, and careful bandwidth choice selects optimal frequencies. Finally, Section 03 covers noise, which consists of unwanted random signals that corrupt information. Noise is classified into four main categories: thermal noise from random electron motion, induced noise from external electromagnetic interference, crosstalk, which is signal interference between adjacent wires, and impulse noise from sudden high-energy spikes. Thermal or white noise is produced by the random motion of electrons in a conductor, a function of temperature. This noise is unavoidable in all electronic devices and transmission media, and cannot be fully eliminated. Induced interference is caused by external electromagnetic sources acting as transmitting antennas. Common sources include electric motors, fluorescent lights, and other heavy electrical equipment. Signal bleeding, or crosstalk, occurs when a signal from one channel affects an adjacent channel due to electromagnetic coupling. This is often noticed as hearing faint conversations from other lines in old telephone systems. Impulse spikes are sudden, high-energy spikes of very short duration. They are mainly caused by lightning, power surges, or switching devices, and are a major cause of burst errors in digital data transmission. Signal-to-noise ratio, or SNR, quantifies signal quality by comparing signal power to noise power. A higher SNR indicates superior signal quality and less data corruption. SNR is commonly expressed in decibels, or dB, a logarithmic scale. The formula is SNR_dB equals 10 times log base 10 of the ratio of signal power to noise power. Low SNR leads to poor communication quality, a high bit error rate requiring frequent data retransmissions, difficulty in signal reception, and reduced achievable data rates. Strategies for noise mitigation include using shielded cables to block external interference, filtering to remove noise-only frequency ranges, and proper grounding to reduce internal hardware circuit noise. In summary, transmission impairments, attenuation, distortion, and noise degrade signal quality. SNR is key for measuring signal health And techniques like amplification, shielding, and equalization ensure reliable communication.